Hello. Today we will start the second module under the topic of optimization. And this module is on the synthesis of resource conservation networks using a superstructural approach. So before we begin, I'd like to acknowledge Professor Dominic Fu from the University of Nottingham, Malaysia, for the as the author of the slides. So we will go back to our topic on water resource conservation networks. Before we use the graphical pinch analysis um, to target and design water conservation networks, and we use and in that topic we have two types. We have the uh, strategy that only uses reuse or recycle. And then another approach is using regeneration reuse, and regeneration recycling. So that again, just a review, the difference is that in direct reuse and direct recycle, there's no need to um, increase the quality of the waste water stream before reusing or recycling it. It's directly used after it becomes a wastewater stream. But in regeneration, there's an intermediate step wherein after it becomes um, after it becomes a wastewater stream, the quality is improved by another unit process, and then that's the only time it's reused or recycled. For the first section, we will focus on the direct reuse and direct recycle. So the direct reuse and direct recycle, whereas the other uh, section, we will also deal with the part wherein there's regeneration. I've shown this before in the previous lecture, which is the superstructure representation of sources and sinks. So sources would be the wastewater that we will reuse or recycle. So those are the sources, and the sinks are the processes that need water. Okay. So we designate the sources by SR and the sinks by SK for this lecture, just like before. And this is the graphical representation of that. In tabular form, it would look like this. And as you will notice, there is an additional stream here, FR, which refers to the freshwater stream. And also by the way, the the column, the first column refers to the water sources, okay, and the row refers to the water sinks. So F would refer to the flow rate, Q would refer to the quality. And we also have at the last column um, the wastewater stream. So any water source that is not reused or recycled goes to the wastewater stream. Okay, so it's designated with the subscript D, while the freshwater is designated with the subscript R. So what do we mean by, for example, the first this cell that I'm referring to? The subscript is R1 SK1. So this would refer to the flow rate from source 1 to SK1. Whereas this cell right here would refer to the flow rate from the freshwater source to SK1. So our main goal is to minimize the freshwater source because it has additional cost, and also minimize the wastewater stream or the unused or unreused or unrecycled wastewater, because treating the wastewater also has cost. And this is our optimization model. We'll be using mathematical optimization. So as I've mentioned, our objective function is to minimize the fresh water source, designated as FR. And um, what is FR? It's the summation of all the flow rates from the freshwater source to each of the sinks. So it's the summation of this uh, row from here to here. And the rest of the equations or inequalities are the constraints. The first constraint refers to the process sink balance. Since in the given problem, the process sinks would require water usage. So the sink balance would consist of the summation of all the connections from source I. So by the way, we use I for the source. We use the index I for the source and index J for the um, sinks. So summation of all the source I to sink J plus of course the freshwater to sink J. And we iterate that for all of the J. So going back to our tabular form, it's the summation from here to here. And we do that for all of the sink from sink 1 to sink J. Okay. The next is the quality requirement of the process sink. So actually, I think if we're talking about wastewater, just like our previous example, if Q is the contaminant, then this sign right here should be less than or equal to. So if the sink has a uh, requirement for the maximum um, contaminant requirement, then this should be less than or equal to. So uh, the summation of the quality of contaminant for each of the connection for each flow from source to sink, and also the quality of the freshwater source. And this term would usually, if we have a good freshwater source, this term would just be 0. So we multiply that Q for each of the, multiply Q to each of the source, and we get the sum that should be less than the product of the flow rate of the sink and the quality of the sink. And then we also have the wastewater balance. I'm sorry, see, so this is the sink balance. This is the source balance. So the we take the sum of all the flow sources and flow from source I to sink J, and also the um unused wastewater, that would be the wastewater for all of the sources. So we just simply sum uh this row from here to here for all, and we do that for each of the sources. Next, these are the non-negativity constraint wherein all of the flows should be greater than or equal to 0. Let's look at an example. This is the same example that we solved during our water um, targeting and design, if you will remember. It's the AN production. AN production, and this is our water sinks. If you remember the boiler feed water and the scrubber are the sinks here and this one. So they require water right here. And we have the sources. So the sources would be uh the this off-gas condensate, the aqueous layer, the bottoms, and also this condensate. So these are the sources of the wastewater to be reused. Um, okay. So we have a matrix right here. Let me, as you can see, as you will notice, this is a blank. What's the reason why is it blank? It's because there we don't directly um use the fresh water as wastewater. So this is illogical if we put a value right here. So it does not directly go to wastewater. Okay. And then what we do, the first thing that we do is to fill out this tabular data with uh, the data that we have from the process flow diagram. Okay, so I skipped the part wherein we obtain this data from the process flow diagram. Just refer to the uh, lecture on water recovery networks. So, so there we inputted the data. The next step is to formulate the model. Uh, so our model, our mathematical formulation is actually this one. Uh, this is our mathematical formulation, and we translate it to lingo. Okay. So obviously, uh, we have the objective function, which is to minimize the freshwater flow rate. We have the flow rate balance, and also the the sink balance, and the quality. This is the sink balance, and then the quality constraint, and the source balance, and this is the total wastewater flow rate. Okay. By the way, these are incomplete. I will leave it up to you to complete. So some of the lines in the code are covered so that you will complete. I will complete it in your as an exercise using Lingo. Okay. So and a challenge for you is to do this in using sets if you can. Okay. Convert the code into sets. Oops. So all right. So after solving the problem, you should get the following answer. Okay, it's a linear programming model. The objective value is this one. So this would refer to the freshwater flow rate. And these are the streams that will reuse or recycle. Okay. Comparing the answer with uh, the graphical or the pinch solution, actually the answer are the same. Let me zoom in if I can. Let me. So in the pinch method, what we obtain is 2.1 fresh water and 8.2 wastewater. So please refer to our previous lecture on the pinch method for this problem. And that is also what we obtained using mathematical optimization. This is for fresh water, this is for wastewater. And another technique that can be used is the automated targeting model, but I haven't taught you this one. Actually, we can skip this topic if we, since it's a supplemental topic, but all the answers match with those three methods. And the network, okay, would appear like this. Okay. So uh, the advantage of using mathematical programming is it already gives you the design of the network. Whereas in the graphical approach using pitch analysis, there are two steps. This one, the first step is targeting. And then if you will remember, we use an algorithm to design the network. I think nearest neighbor algorithm. But for mathematical programming, uh, the model already outputs this one. So there's an advantage and disadvantage for both approaches, right? Because as you can see from here, you have to translate that into this form. So, but there's a technique to export the data to Excel, which I will show you. Okay, so I'm showing the Lingo model of example 12. Here you have to include this code in order to print the data in Excel. So I made an example right here wherein you can output the value of FW and WW to Excel. So what you need to do is after typing this data, you have to go to Excel and then under let me wait, under date. So for example, this is FW and WW. So if this is the cell wherein I want the data to appear, so under formulas, define names, define name. You can define this as FW and this one as WW. So uh, this one, this part of the code right here. Okay, let me go back to Lingo. Okay, this part of the code would refer to the variable name, while this part of the code would refer to the name in Excel, the cell name in Excel. So again, this is the variable name, this is the name in Excel. So when I solve the problem, okay, you can go to Excel. Oops, did not appear. Okay, let me try that again. Define name, define FW. Okay. Ah, okay. Define names, name manager, the FW and WW. Hmm. Wait. So okay, so hold on for a while. Okay, so let's assume first I remove the so before there's an end code right here, so I remove that. And next you have to save the Excel file. Okay. So I save the Excel file as a file. Okay. So let's try that again. Alright, so it succeeded. Then now I check the Excel file. It's now populated. Okay. So if you're not going to use sets, then you have to uh, repeat this code for every variable for F11, F12, so on and so forth. Okay, you have to repeat it. Uh, but if you're using sets, then um, you just simply input the name of the variable. So let me demonstrate that. Okay, so for example, this is a version that used sets for the same problem. And for the flow rates, I named the variable as F. Okay, so F. By the way, I use different names. FW for wastewater, FR for freshwater, so don't be confused. Um, Now I want to output the variable F. Okay, so just to show you first, this is the variable F. I um I want to automatically export all of the values for F. I only need one code for that since I'm using sets. So in Excel, I have to allocate, since the number of F variables are 8, then I have to allocate, let's put it here, 8 cells. I have to name them uh, F value, the same as I named in my sets right here, F value. So it will output F. So when I solve it right here, then I go back to Excel there. So this is the output. It automatically populated the 8 cells for the connections between the sources and sink. So that's how you output. That's how you output or export Wave to Excel. Alright. Alright, so in my export to Excel, I only generated these values, but you can also export these values as well. Okay, let's proceed. Okay, so in this slide, it's just shown the freshwater flow rate and the wastewater flow rate as well as the wastewater concentration, which was computed manually. Okay. What if we want to force a design? When I say force, for example, we don't want sink source one and sink one to have a connection. That's why there's an X mark here. But we want that connection between source one and sink two. So what we can do is to add an additional constraint. Okay, so for we just add an additional constraint. If you're not using sets, okay, you can directly use this constraint F11, F12. If you're using sets, then you have to determine the variable name um, assigned by Lingo. And you can do that in the generate model under options tab. Okay. So if you're not using set, just add this to force the connection between, to forbid the connection between source 1 and 2 and force the connection between source 1 and sink 2. Okay. So after doing that, you will notice that the point 8 here is transferred to the connection between source 1 and sink 2. So that you can do that. Now at this point, you can pause the video and try it for yourself. If you're done with that, we can proceed with the next topic, which is on capital and total cost estimation. Okay, so uh, the capital cost correlation, not sure if you study this in your equipment design uh, or plant design before. So we have the capital cost correlation equation wherein A, B, and C are constants depending on the material, and F is the capacity of the equipment. So it's just an estimation of the capital cost. And you can find the values for A, B, and C from the literature. So depending on the equipment and the type of material. Now, we can use a binary variable to incorporate um, into the capital cost calculation. So it's used to uh, de- define the presence or absence of the flow. Okay. So the binary term would either have a value of 0 or 1. If the value is 0, then there's no connection. And if the value is 1, then there's a connection between the source and sink. So um how do we assign 0 or 1, okay, to our binary variable? We can use this code right here. So remember, uh, FSR and FSR FSK. So this term right here represents the connection between source I and source J. So if the connection is 0, that means there's no flow. But if it's greater than 0, it means there's a flow. So if it's 0 divided by m is an arbitrarily large number. B this variable would be 0. So it will represent that um, there's no connection between source I and source J. However, if there's a value here, that non-zero value, either zero point 0.1 or 1 or whatever non-zero value, this binary variable will automatically be assigned a value of 1. So what's the relevance in the capital cost? Okay. So if there's no connection, then this term C bin would just be 0. But if there's a connection, regardless of the flow rate, okay, automatically we there's a pipe. Okay, there's a pipe requirement to connect source 1 and sink 1, and therefore that pipe should be included in the capital cost. So I hope that's clear. So if there's a connection, bin would be 1, um, and automatically this would activate that this term uh, because there's a piping requirement for that flow rate. Okay. And then we also need to know the concept of annualizing factor. So I hope you remember that from your equipment or plant design. Uh, so the annualizing factor is the capital cost should be multiplied by the annualizing factor. Okay. And the annualizing factor is calculated using the formula. Okay, this formula where IR is the annual fractional interest rate and YR is the number of years. So why do we need to convert the capital cost to, or why do we need to multiply it with the annualizing factor so that it will be converted into, the cost will be converted into annual cost. Okay, because our operating cost uh, is based on the annual operating cost. So if we want to know the total cost, then we have to annualize the capital cost as well. Okay, so I hope that's clear. So again, the capital cost is the bulk when you buy like an equipment or a building or whatever. But the uh, operating cost is uh, evaluated annually. So you have to convert the capital cost you have to evaluate it annually. So converting it to annual cost by multiplying it with annualizing factor, so that you can add the two, capital cost plus the operating cost. The operating cost is the annual operating cost is determined by multiplying the operating cost and the annual operating time. So if the operating cost is per second or per hour, you have to convert it into per year, and that is the annual operating time. So how do you calculate the operating cost? Um, you can do that by, in our case, it's the cost of the fresh water and the cost of treating the wastewater. So since our flow rates, right, in the problem is per second, I think. Yep, it's per second. Then we convert this to annual by using the factors, annual operating time. Okay, so this is how we look at the annual operating cost. Finally, to calculate the total annual cost, you have to add the annual operating cost with the annualized capital cost. Okay, so that's the capital cost times the annualizing factor. Now we move on to the example. Uh, so before we move to the lingo code, we have to de determine the operating cost, capital cost, and the minimum. And with those two, our objective function is to minimize the total annual cost. Okay. So given the following data, the cost of both fresh water and wastewater is this $1 per ton, and the piping cost is given by this following equation. So the piping cost would the pipes would run from the reuse and recycle streams, and also between the fresh water and the sinks, and of course the waste streams also. Uh, okay, so this is the piping cost, and okay, here you'll see the presence of a binary variable. So um, and also F is the flow rate between the flow rate of the streams. Okay. So if the flow rate is non-zero, so there's an additional 250 in the cost. And you have to multiply that with the distance between the water sinks and water sources. Okay. And also another data is the annualizing data, which is a period of 5 years with an interest rate. So you have to use this formula to calculate the annualizing factor. And the annual operating time is 8,000 hours. So this will go into that one. As for the data on the distance, here it is. So let me correct myself. There's no piping requirement to the wastewater based on the data. So we only have the distance between the sink, the fresh water, and the sink and the sources. Okay. So we go back to the same problem. Uh, but now we have an additional variable, which is the binary variables. So for each of the connection, there is a representative binary variable, which you have to populate. Let's go to the lingo code. Again, the um, objective function is to minimize the total annual cost. And the total annual cost is the annual operating cost. This is for the fresh water and wastewater treatment plus the piping cost multiplied by the annualizing factor. So it's already computed here, but you can check if this is correct. The operating cost is converted to, since this is per second, the flow rates are per second, converted to hours and then to year. This is the annual operating hour, 8,000 hours per year. Next, this is the operating cost, the flow rate of the fresh and wastewater. This is the cost. And then we have the piping cost, which is the total. So there's the piping cost of the waste, ah, fresh water to sink one, fresh water pipe from freshwater source to sink one, freshwater to sink two, and then the connections between the sources I to source to sinks J. Okay. Next, one by one, these piping costs are uh, coded. So you have to complete this on your own via Lingo. And we have an additional uh, constraint. Okay. For the binary variables. So notice that these are our binary variables, and we use the following equation in inequality to generate the binary variable. So depending on the value of the flow rate, this will either be 0 or 1. And depending on the value of the binary variable, this term right here will be either 0 or 1. And we have to define the binary variable. You have to include this code, okay, to make sure that uh, these are the binary variables. Otherwise, the default in Lingo is that the variable is continuous. So you don't want that. These are already the results of the optimization. So, of course, this code is incomplete. You have to include the code from the previous exercise, except the objective function. You remove this one and you add the code, okay, for this one to consider the annual cost. And what you will get should be equal to this values. So let me open that for a while. This is the Lingo code. I did not convert it to sets, but if you want, you can convert it to sets. So now I will run it and let's see if I got the same answers. Yep. So based on the slides, total annual cost is 302,000. So it's the same. Okay, so you try it yourself. Okay. By the way, I retained the code that forbids the match between source 1 and source 2. Okay. Alright, so at this point, you may pause the video and see if you can generate the same results. If you're done with that, we can proceed to the next section, which is reducing network complexity. So for example, you want to have less piping connections, then you may impose a maximum number of uh, connections. Say for example, you want to just limit the connection to 3. So this would be 3. I will assign it to 3. And another constraint is if you want to set a minimum flow rate, because if the flow rate is too low, then it might not make sense to invest on piping for that flow rate. So you can set a constraint that would force a minimum flow rate. Okay. Example, you assign that as the minimum flow rate as F min, then you can input this code. For example, let's try this one. Uh, you want to the maximum, you want to set that the maximum reuse recycle is just limited to 1, and the minimum flow rate is 1 kilogram per second. And also, you still want to retain this compulsory connection between source 1 and sink 2. Okay. What you can do is to uh, to include this code right here. Fmin, so Fmin is equal to 1. So you can, and also you can include this. So this first code set of codes here is for the minimum flow rate, and the second set of code is for the piping. Okay, so what will happen is that it will change the total annual cost. Let's see if it's lower to higher. Okay, to higher than before. Okay. But because it increased the annual operating cost. Okay, so uh, these are the results. So I hope that you got the same results. Let me open my own version of the, let me see if I get the same. Okay, so I'm showing the lingo code for example 12.4. Let me run it. So the total annual cost is 346,000. I think yeah, it's the same answer with this one. Oh, so by the way, notice that the model class is now mixed integer linear programming because there's a mixture of continuous and binary variables. Okay. And this would be the connection for the optimal solution. So please check if you got the same. And this would be the quality of the wastewater. Okay. At this point, you can pause the video to try it yourself. So if you're done with that, we can move on to the next topic, which is the part uh, where regeneration is required. Okay, so here cannot directly reuse or recycle use or recycle our streams, but there's an intermediate step which is the regeneration. Okay, so we represent that in the superstructure figure as interception. So before the sources go to the sink, they have to uh, some of the source have to go to the interception. Okay. Since this is a superstructure, okay, it just shows that all of the possible connection. Okay, so even the direct connections are shown and also the regeneration connections are shown. Remember, superstructure representation shows all possible connections. And how will it look like in the tabular form? So it would look like this. There's a regeneration row and column, okay, wherein there's a connection between each sink with the regeneration and each source with the regeneration unit. Okay, there will be a slight change in our uh, mathematical model. The addition of the regeneration term for each sink and uh, of course the quality as well and for each source. So it's the same as before, we only added this one and also a flow rate balance for this one is also new, flow rate balance for the interception unit. And also this one, all variables should be non-negative. Okay, so we try the next exercise. There are two options to minimize the cost, option 1, and option 2 to minimize the flow rates with two-step approach. What do I mean by two-step approach? First, we minimize the freshwater flow rate, and then after that, we obtain this minimum value. In the second step, we minimize the regeneration flow rate with the additional constraint that what we obtained from the first step, we assign that as the fresh water flow rate. Okay, so let's try it using this new data from Wang and Smith. This is example 12.5. So using this data, the task is to generate or synthesize a water regeneration network. A single pass interception unit with outlet concentration 5 ppm is used to purify the water sources. So there's a regeneration unit and its output is 5 ppm. There's also fresh water available for use. Okay, there are three cases. Case 1 is to determine the minimum operating cost given the following data. Case 2 is to minimize the flow rates for both freshwater and regeneration source. So you have to do the two-step approach. And case 3, redo case 2, but you have to accept only maximum of 2 reuse recycle connections for ease of process control. Okay, so here we can actually we are allowed to still have direct reuse and recycle, but we have a regeneration unit. Okay, so this is our uh, superstructure network in tabular form. And also we have the data right here. And here will be our Lingo model. Okay. So I leave it up to you to generate your own model. Okay. Let's see case 1. So case 1, we minimize the cost. Okay. Case 1, let's see, minimizing the cost. I will open my own. Hold on for a while. Okay, so I'm showing now the Lingo code. So this one is the um, cost of fresh. All right, wait. The cost of freshwater and wastewater are $1 each. And the cost of the regenerated water is $0.8 per ton. So in the code, we have to write that freshwater times 1, regeneration times 0.8. So let's see if I got the same answer. Yep. So this is the objective function. Dollars. $98. Okay. So this is for case 1 right here. And you should have the same connections. Okay, so please check. You got the same connections. Now, can you check that? Just compare the values here. Okay, with that in the slide. So all of these values here. There. Next is the case 2, two-step. So first is minimize the freshwater and then assign it to freshwater and then minimize the regenerated. So I'm showing the Lingo code. Okay, let us see. So the minimum reg is 73. So correct. The answer is 73. Okay. So I hope that you also get the same answer. And finally, uh, case 3, there's additional code. So in case 3, let me go back to the requirement. So there's a requirement to uh, limit the reuse recycle connection to 2, meaning these connections between sink and sources limited to 2 only. So with that, we have to assign to um, create new binary variables. Okay, so we do that using the equation, inequality, to create the binary. I mean to assign either 0 or 1 to the binary variables, and each processing can only accept 2 reuse recycle. So for each sink, for each sink, the sum of this binary variable should be less than 2. And then, of course, we have to define the binary terms. And the answer is here. So as you can see, each sink, each column here has only maximum of 2 connections. Okay, so let me open my Lingo. I am sharing the lingo. Okay. Not sure if I was able to, let me check. Okay, so each sink should have a maximum of two. So I'll let you check your answer on your own if you were able to get the same answer as the example. So at this point, you can pause the video to try it out for yourself. Okay, for the next topic, this is not a requirement, but it's an interplant resource conversion network. So it just connects one plant to the other. But I will not require you to do the exercise for this. But as you can see, the superstructure network is much more complex because there's another plant. Okay. And in the tabular form, there are interplant regions. Okay. You also need to add, just like in the regeneration, there's an additional term in the balances for the interplant connection. So the, um, these are the objectives that you can do. You can minimize the cost or minimize the flow rates using the two-step approach by first minimizing the fresh resource water fresh water across all plants, and then getting that data and then minimizing the cross plant stream flow rates. You can try it out for yourself. This example has two networks. I mean, yeah, two plants. This would be the exercise. The problem. And this is the superstructure. Okay, so that's the answer. I don't have the code for this, so it's up to you. I will not require. I just only require until exercise uh 12.5. Okay. But 12.6 is optional. All right, so this ends the second module under optimization. I will end the video and see you next video.